Let's take a look at the mathematical model that we need to solve. The mathematical model is a boundary value problem, as in a lot of engineering problems. And boundary value problem is governing equations defined in a domain and boundary conditions defined at the edges of the domain. And the governing equations in this case are partial differential equations. We'll take a look at the governing equations first, and then we'll take a look at the boundary conditions. The governing equations are based on the physical principle of equilibrium of an infinitesimal element, that is a vanishingly small chunk of material. So if that is my chunk of material, and I'm showing you a two-dimensional view to keep things simple, and let's say that's delta x, that's delta y, we are looking in the limit as these tend to 0. That's the trick in calculus. And we say, that vanishingly small chunk comes to equilibrium, so it has no acceleration, and so the forces on it have to balance. It becomes a free body diagram on that vanishingly small chunk. On the left side, my forces are proportional to the normal stress, the forces in the x direction. And on the right side, the normal stress is slightly different, and that difference is proportional to the gradient of sigma xx in the x direction. Similarly, I can look at the shear stress on this face, and then the shear stress on the top face is slightly different, and it's proportional to the gradient in the y direction now rather than in the x direction. And so when I do the force balance, I get the differential equation of equilibrium in the x direction. And this is essentially the force balance per unit volume. So the delta x, delta y, etc. drop out. And so this term comes from here. That term comes from here. That term comes from a shear acting on this face and a corresponding face at the back. And then that's a body force. And I talk about this in the big ideas in solid mechanics in more detail. And you can do a similar gymnastics in the y direction and in the z direction. And by the way, in other places, I've used a slightly different notation. The normal stress, sigma xx, I denote as sigma x, and the shear stress I denote as tau xy. And you will see this notation too. So the textbook I've used before was using this notation, and the textbook I'm using currently is using this notation, and also the course for which I'm developing this module is using this notation. So I have three partial differential equations from the force balance on this vanishingly small chunk in the x, y, and z directions. I have 6 unknown functions, 3 normal stresses, 3 shear stresses, and keep in mind that each stress component is a function of x, y, and z. It's a three-dimensional problem. So we need additional equations to close our equation set. We can bring in a set of additional equations from the 3D Hooke's law. So we have 6 equations written in matrix form relating the stress components to the strain components. And so we have 6 additional unknowns over here. So I've added 6 equations, but I've also added 6 unknowns. So my equation set is still not closed. And I'm assuming that the material is in the elastic range, because stress is directly proportional to the strain in this relation. And I have 2 material properties, Young's modulus and Poisson's ratio. And the Young's modulus, I'm assuming, is the same in all 3 directions. So I also have an isotropic assumption embedded in there. Okay, so I need another set of additional relations, which I'll get from the strain displacement relations. And so the 3 normal strains are related to the displacements in this way, and the 3 shear strains are related to the displacements. So I have 3 additional unknowns. Think of this as 3 additional unknowns, u, v, w, but I have 6 additional equations. So now my equation set should be closed, and we will take a look at that in the next video.